In this video, we're going to prove or maybe derive the law of cosines. So similarly to the law of sines proof, I'm going to start off with just a generic triangle ABC. So I've just drawn triangle ABC. It could be isosceles, it could be right, it could be whatever triangle. And I've labeled the corresponding or the opposite side lengths with the same letter but lowercase. And similar to the law of sines proof, I think I'm going to start off with constructing that altitude. So I'm going to draw H, again, the altitude of this triangle. So from angle C or vertex C, I'm going to draw the altitude, which is just a line that hits lowercase c at a right angle. And by doing so, I've created two right triangles within my original triangle ABC. Now, some things I'd like to notice. If I want to start talking about cosine, so cosine of angle A, well, the SOHCAHTOA definition of cosine requires the adjacent side length over the hypotenuse. And at this time, I don't know the adjacent. The adjacent refers to the distance from angle A to where the altitude hits little c, or this line segment AB. Well, I can do something. I can create a variable to talk about that adjacent side length. So let's call this distance x. Then I can refer to x as my adjacent. So cosine of angle A would be the adjacent over the hypotenuse, x over b. Now the law of cosines, I think, is going to be similar to the law of sines, where I'm able to relate a, b's, and c's, but maybe not these random variables like x, which has nothing to do with triangle ABC. So I'm going to do one more step here, and that is solve for x. I'm going to multiply both sides of the equation by b. So x is equal to b times cosine of a. Okay, cool. All right, next thing I want to do or play around with is I'm going to use the Pythagorean Theorem to relate b, h, and x. So if I take a look at just this triangle here, A, C, let me maybe label this D, ADC, then I'm going to do the Pythagorean Theorem with that triangle, ADC. So that is the two side lengths squared and summed. X squared plus h squared will equal the hypotenuse of that triangle squared, so b squared. And I'm going to go ahead and solve for h squared, kind of similar to the law of sines, where we were solving for h. I'm just going to solve for h squared. So h squared is simply b squared minus x squared. All right, I'm going to do that again. I'm going to play around with Pythag once more, but with this other triangle. So BDC, okay, well, all of a sudden I need this distance now. So I don't want to create another variable like y or z. So I'm going to try to relate the distance from D to B using only the variables I have. So if the entire base adds up to c, or measures c, and this little bit measures x, then I can say that from D to B, that would be the total minus that bit. So I'm going to call that c minus x. And I'm going to play around with Pythag again. So c minus x quantity squared plus h squared will equal the hypotenuse a squared. Oh, I know h squared. H is equal to this. So I'm going to make that substitution. H squared can be rewritten as b squared minus x squared. I'm going to substitute. So I have the quantity c minus x squared plus b squared minus x squared, and that is equal to a squared. All right, I'm going to, expand that out. So if I have c minus x squared, that's a perfect square trinomial. So I have c squared minus 2cx plus x squared. Now I'm just going to copy all this down. Plus b squared minus x squared, and that's still equal to a squared. Looks like I have like terms. Positive x squared and negative x squared will cancel to 0. And then I have this single x. And again, my goal here is to create a relationship between a's, b's, and c's, not that x. So I think what I'll do here is substitute what x is in terms of a and b. So x can be rewritten as b cosine a. So in this next step, I'm going to make that substitution. So I have c squared minus 2c times b times cosine a plus b squared equals a squared. This equation, or this relationship, is extremely powerful. Again, I have created this relationship with a's, b's, and c's at an angle A. These are all variables on the original triangle ABC. Again, ABC was just some generic triangle that did not have right angles. Up until now, when we were trying to solve triangles, we had to deal with right triangle trig. But with this relationship, I no longer need those right angles. I can solve this triangle even though it's not right. Now, typically you'll see this written more prettily, so I'm just going to rearrange it. I'll write the a squared on the left, or just kind of flip-flop this, and then I'll put this in alphabetical order. So you'll typically see it written as a squared is equal to b squared plus c squared minus twice their product, BC, times cosine of an angle, and that angle is always going to match the variable that's by itself, so cosine of A. We call that the law of cosines. And again, if I had just drawn my altitude from a different angle, instead of from angle C, if I had drawn it from angle A, I would come up with a very similar relationship written as such. So the law of cosines, there's 3 versions. It kind of depends on which angle you're looking for, maybe which situation you're in. But I've got this one here. A squared is equal to b squared plus c squared minus twice their product, got the squares, times cosine A. B squared follows the same format. It's equal to the other 2 variables, summed and squared, minus twice their product times cosine of that matching angle. Similarly, c squared equals the other 2 summed and squared minus twice their product times cosine of that matching angle. All right.